Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on September 4th, 2025, just yesterday. The striking result is simple and powerful. Reinforcement learning fine-tuning reaches the same new task performance as supervised fine-tuning, yet it forgets far less of the model's prior skills because it gravitates toward solutions that stay closest in forward KL-Divergence to the original model. The paper is titled, RL's Razor, Why Online Reinforcement Learning Forgets Less, and the implications for model training are quite significant. In short, the work spans large language models and a robotic policy, links forgetting tightly to forward KL-Divergence, and explains why on-policy updates preserve earlier capabilities. On X, reactions spotlight the KL minimal bias idea. One post highlights that reinforcement learning keeps performance on out-of-distribution tasks by staying close to the base model. Another thread debates on policy versus off-policy data and important sampling trade-offs. Engagement looks solid, with a leading post drawing about 646 likes, while others show modest but interested replies. Alright, the previous segment summarized the core claim. Figure 1 illustrates it visually. The left panel shows trajectories from the base policy, where reinforcement learning heads to a region of high new task success that stays close in forward KL, while supervised fine-tuning drifts farther. The right panel plots retention versus new task performance, and the dashed red curve sits consistently above the blue curve, which means less forgetting at the same accuracy. So the previous figure set up the intuition about retention. Figure 2 presents Pareto frontiers that plot new task accuracy on the x-axis against average score on previous tasks on the y-axis. The red dashed curves for reinforcement learning stay high across accuracy ranges, which indicates strong retention at matched new task gains. The blue dashed curves for supervised fine-tuning bend downward, so higher new task accuracy comes with larger drops on prior tasks. The pattern holds across math, science question answering, tool use, and a pick-and-place robot. Alright, the previous figure contrasted retention across tasks. Figure 3 dives into parity MNIST and shows three linked views that explain why forgetting tracks forward KL. The left panel plots new task accuracy versus prior fashion MNIST score and shows reinforcement learning lying on a flatter frontier, while supervised fine-tuning drops sharply unless an oracle labeling is used. The middle panel collapses methods onto one curve when forgetting is plotted against KL, which signals KL as the driver. The right panel shows accuracy rising with much smaller KL under on-policy updates. So the previous figure tied forgetting to forward KL. Figure 4 compares four training setups across two axes, on policy versus offline, and whether training includes negative examples. The middle scatter shows that on policy methods reach the same accuracy with much smaller KL, which signals more conservative updates. The right panel plots retention versus new task accuracy and shows flat, higher curves for GRPO and 1-0 reinforce, while SFT and SimPO bend downward. So, the previous figure tied forgetting tightly to forward KL. Table 1 quantifies that by comparing candidate predictors of forgetting on the MNIST setup. Forward KL tops the list with an R-squared near 0.96 using a quadratic fit, which means it explains most variance in retention. Reverse KL and total variation trail behind, and weight or activation changes sit far lower, so internal drift alone does not predict forgetting. The takeaway is that distributional distance in the forward direction is the reliable signal. Okay, two takeaways stand out. Reinforcement learning fine-tuning preserves prior skills because on-policy updates gravitate toward KL minimal solutions, and forward KL on the new task distribution reliably predicts forgetting across domains. The broader implication is practical. Control forward KL during post-training to adapt safely without erasing capabilities. That is it for the AI Research Roundup. I am Alex. Thanks for listening.